On December 27, 2004, something 50,000 light-years away changed the chemistry of Earth's atmosphere in less than a second. Not a supernova, not a gamma-ray burst, not a black hole. A dead star, no larger than Manhattan, released more energy in 1/10 of a second than our Sun will produce in 100,000 years. The radiation wave hit Earth with such force that it compressed our planet's magnetic field and ionized the upper atmosphere. Satellites failed, radio telescopes overloaded. For a moment, astronomers thought we were under attack. But this wasn't an attack. It was a warning shot from the most extreme objects in the known universe. What if I told you there are stars out there with magnetic fields so powerful they would pull the iron from your blood at a distance of 1,000 kilometers? Stars that experience star quakes violent enough to crack nuclear matter. Stars that shouldn't exist according to everything we thought we knew about the laws of physics. Today, we journey through evidence that challenges everything we understand about matter, magnetism, and the violent death of stars. Prepare yourselves. We begin.
March 5th, 1979, 10:51 a.m. Universal Time. Soviet spacecraft Venera 11 and Venera 12, designed to study Venus, suddenly registered an impossible surge of gamma radiation. Seconds later, instruments aboard American satellites lit up like Christmas trees. Within moments, every spacecraft in the solar system capable of detecting high-energy radiation was screaming warnings to Earth. Something had hit us. The burst lasted less than a quarter of a second, but it was unlike anything astronomers had ever recorded. It wasn't coming from inside our solar system. It wasn't the Sun. The signature was wrong for a supernova and far too brief for any known stellar explosion. Dr. Tom Klein at NASA's Goddard Space Flight Center was among the first to analyze the data. What he found defied explanation. The energy wave had traveled across interplanetary space and overwhelmed detectors designed to study the Sun's relatively gentle radiation. Whatever created this burst had released more energy in 200 milliseconds than our Sun produces in several thousand years. But here's what truly baffled scientists. The radiation came in waves, pulsing every 8.1 seconds with the regularity of a cosmic heartbeat. The source was eventually traced to the remnants of a supernova in the constellation Dorado, a stellar corpse about 20 kilometers across, a neutron star. Now, neutron stars themselves are already exotic. When a massive star explodes, its core collapses with such violence that protons and electrons are crushed together into neutrons. The result is a sphere of pure nuclear matter, essentially a giant atomic nucleus the size of a city, containing more mass than our entire Sun. Imagine compressing Mount Everest into a sugar cube. That's the density we're talking about. A teaspoon of neutron star material would weigh approximately 10 million tons on Earth, more than all the cars, trucks, and buses in the United States combined. But this object in Dorado was different. Traditional neutron stars, pulsars, emit steady beams of radiation as they spin, like cosmic lighthouses. They're powered by their rotation, gradually slowing down over millions of years as they radiate energy. This thing wasn't following those rules. The burst from SGR 0526-66, as astronomers designated it, released approximately 10 to the 44th ergs of energy in a fraction of a second. To put that in perspective, if you could somehow harness all of humanity's power generation for the entire history of civilization and release it instantaneously, you wouldn't come close to 1% of this event's power output. And it did this while spinning relatively slowly, once every 8.1 seconds. A typical pulsar spins hundreds of times per second. This object's rotation alone couldn't possibly account for the energy it released.
Dr. Christopher Thompson and Dr. Robert Duncan, working at different institutions in the 1990s, independently arrived at the same outrageous hypothesis. What if some neutron stars possessed magnetic fields 1,000 trillion times stronger than Earth's? What if these fields were so intense they could power eruptions that made supernovae look like camera flashes? They called these hypothetical objects magnetars. But the evidence forces us to confront an uncomfortable possibility. These aren't hypothetical at all. They're real. They're scattered throughout our galaxy, and occasionally they wake up. In the decades following the 1979 event, astronomers detected approximately 20 more similar bursts. They called them soft gamma repeaters, SGRs, because unlike other gamma-ray sources, these objects erupted multiple times from the same location, and the radiation was softer or less energetic than typical gamma-ray bursts from distant galaxies. But the real breakthrough came from space-based observatories like NASA's Chandra X-ray Observatory and ESA's XMM Newton. In 1998, astronomers using the Rossi X-ray Timing Explorer made a crucial measurement. They detected the slowing of SGR 180620's rotation. This neutron star was losing rotational energy at a rate far exceeding what could be explained by radiation losses alone. The numbers were staggering. SGR 180620 was slowing down 100,000 times faster than ordinary pulsars of similar age. Something was draining its rotational energy at a catastrophic rate. The answer lay in the magnetic field. Using observations from multiple satellites, scientists calculated the magnetic field strength of these objects. The results seemed impossible: 10 to the 15th Gauss. That's a 1 followed by 15 zeros. To understand this number, consider this. Earth's magnetic field, about 0.5 Gauss. A typical refrigerator magnet, 100 Gauss. The strongest magnetic field ever created in a laboratory, approximately 100 million Gauss, sustained for a few microseconds before the equipment destroys itself. A typical neutron star, 10 trillion Gauss. Magnetars, 10 quadrillion Gauss, 1,000 times stronger than ordinary neutron stars. At this field strength, physics breaks down in spectacular ways. Dr. Sergei Popov at Moscow State University calculated what would happen to a human near a magnetar. The results are genuinely disturbing. At a distance of 1,000 kilometers, still in space, nowhere near the surface, the magnetic field would be strong enough to fatally disrupt the biochemistry of your cells. The field would distort the electron clouds around atoms in your body, rendering molecular bonds unstable. You wouldn't be pulled toward the magnetar like iron to a magnet. You'd simply cease to function at a molecular level. But it gets stranger. At this field strength, even the vacuum of space behaves differently. According to quantum electrodynamics, intense magnetic fields can polarize the quantum vacuum, causing light itself to split into two modes traveling at different speeds. Parallel to the field, light moves at one speed; perpendicular to it, another speed entirely. In other words, space itself becomes birefringent, like a crystal, warping light in ways that would make the environment around magnetar visually incomprehensible to human eyes. In 2003, astronomers made another critical discovery. Using data from the Chandra Observatory, they detected something unexpected around several magnetars: twisted magnetic field lines extending thousands of kilometers into space, forming a dynamic magnetosphere that constantly reconfigures itself. These reconfigurations release energy, lots of energy.
Dr. Nanda Rea and her team at the Institute of Space Sciences in Barcelona analyzed years of X-ray observations and found that magnetars aren't just bright in gamma rays during giant flares. They emit steady X-ray radiation 1,000 times brighter than ordinary neutron stars, powered entirely by the decay of their magnetic fields. But this represents just one piece of a much larger puzzle.
December 27, 2004, the event astronomers had been dreading finally occurred. SGR 1806-20, located approximately 50,000 light-years away in the constellation Sagittarius, unleashed a giant flare. The initial spike lasted just 200 milliseconds, but released 10 to the 46th ergs of energy, the equivalent of 2 centuries of our sun's total power output, compressed into less than a quarter of a second. The radiation wave traveled across the galaxy at the speed of light. When it reached Earth, it was still powerful enough to brighten our night sky more than a full moon, despite being 50,000 light-years away. Think about that. A stellar object the size of Manhattan Island, halfway across the galaxy, briefly outshone the full moon in our sky. Dr. Brian Gansler at the University of Sydney analyzed the aftermath. What his team discovered was genuinely unsettling. The flare had cracked the neutron star's crust. You see, a magnetar isn't a uniform sphere, it has structure. A thin atmosphere of ionized gas, a solid crystalline crust of nuclei and electrons about a kilometer thick, an interior superfluid of neutrons, and possibly a superconducting core of exotic matter we don't fully understand. The crust is held together by nuclear forces, making it incredibly strong, millions of times stronger than steel. And yet, the magnetic stresses had fractured it. The event was essentially a starquake. When the crust cracked, the magnetic field lines anchored in that region suddenly reconfigured, releasing magnetic energy in a catastrophic cascade. The surface of the star shifted by mere centimeters, but in a material this dense, that represents the movement of approximately 10 to the 27th kilograms, about the mass of Earth's moon, in a fraction of a second. But the most remarkable discovery involves what happens inside the star. In 2013, Dr. Anna Watts and her colleagues at the University of Amsterdam published theoretical calculations suggesting that the interior of a magnetar might exist in a state of quantum turbulence. The magnetic field is so strong it alters the behavior of the neutron superfluid, creating quantized vortices that interact with the magnetic field in ways that classical physics can't describe. This means the interior of a magnetar isn't just exotic, it's a laboratory for physics we can't replicate anywhere else in the universe. The pressures exceed anything achievable on Earth. The magnetic fields are 1 billion times stronger than anything we can create, and the quantum effects are macroscopic, operating on scales of kilometers rather than atomic diameters. Recent observations have revealed something even more disturbing. Magnetars sometimes exhibit behavior that shouldn't be possible. In 2020, astronomers detected X-ray pulsations from SGR 1935 plus 2154. Nothing unusual there. But then, using radio telescopes, including the CHIME array in Canada, they detected something unprecedented: fast radio bursts originating from the magnetar itself. Fast radio bursts, FRBs, are intense pulses of radio waves lasting milliseconds, previously detected only from distant galaxies billions of light-years away. Their origin was one of astronomy's great mysteries, and here, suddenly, was a magnetar in our own galaxy producing them. The evidence extends beyond simple radio pulses into the realm of genuinely bizarre physics. Some of these bursts showed polarization signatures indicating they passed through magnetic fields so twisted and intense they shouldn't be able to exist under the standard model of particle physics. So how does a neutron star acquire a magnetic field 1,000 trillion times stronger than Earth's? The answer lies in the violence of its birth.
When a massive star, at least 20 to 30 times the mass of our Sun, exhausts its nuclear fuel, it can no longer support itself against gravity. The core collapses in less than a second, rebounding in a supernova explosion that tears the star apart. During this collapse, any magnetic field present in the original star's core gets amplified by a factor of approximately 100 trillion, compressed along with the matter itself. But that's not enough to create a magnetar. Dr. Duncan and Dr. Thomson's calculations suggest that magnetars form only when the newborn neutron star is rotating extremely rapidly, perhaps several hundred times per second, and undergoes violent convection in its interior during the first seconds of its existence. Imagine this. You have a sphere of ultra-hot nuclear matter spinning hundreds of times per second, undergoing turbulent convection driven by thermal energy from the collapse. The churning motion acts like a dynamo, twisting and amplifying the magnetic field through a process called magnetohydrodynamic instability. Within about 10 seconds of the neutron star's birth, its magnetic field can amplify from 10 to the 12th Gauss to 10 to the 15th Gauss, a 1,000-fold increase, powered by the star's rotational energy and convective motion. But here's the catch. This process is so violent and so dependent on precise conditions that probably only 1 in 10 neutron stars becomes a magnetar. The rest become ordinary pulsars.
Dr. Krissa Kovalia-II, working at NASA's Marshall Space Flight Center, led research that confirmed a crucial prediction. Magnetars should have a limited lifetime as active objects. The intense magnetic field gradually decays over thousands of years, dissipating as heat and radiation. As it decays, the field can no longer generate the violent eruptions characteristic of young magnetars. The star enters a quieter phase, eventually becoming a dim, slowly rotating neutron star, indistinguishable from billions of other stellar corpses scattered throughout the galaxy. This forces us to reconsider fundamental assumptions about stellar evolution. Magnetars aren't a permanent state. They're a brief, violent phase in a neutron star's life, lasting perhaps 10,000 years before fading into obscurity. The implications extend far beyond individual stars. In 2008, astronomers using the SWIFT satellite detected what appeared to be a magnetar flare from the Andromeda galaxy, 2.5 million light-years away. If confirmed, the event would have to be even more energetic than the 2004 flare to be visible across such a vast distance. This suggests that magnetar giant flares might be one of the most energetic explosive phenomena in the contemporary universe, rivaling gamma-ray bursts from collapsing stars in distant galaxies. But there's a darker implication. Dr. Adrian Mellett at the University of Kansas published calculations examining what would happen if a magnetar giant flare occurred within 10 light-years of Earth. The results are sobering. The gamma radiation would strike Earth's atmosphere, triggering a cascade of chemical reactions that would deplete the ozone layer by approximately 50% within weeks. Without this protective shield, ultraviolet radiation from the sun would increase dramatically, causing mass extinctions of phytoplankton in the oceans and damaging DNA in surface-dwelling organisms. Fortunately, there are no known magnetars within 10 light-years of Earth. The closest confirmed magnetar, SGR 1806-20, is safely distant at 50,000 light-years. But astronomers estimate there could be 30 million neutron stars in our galaxy, and we've only identified a tiny fraction of them. How many dormant magnetars are lurking out there, invisible in the darkness between stars?
Recent breakthroughs suggest we're on the verge of understanding even deeper mysteries. In 2022, NASA's Imaging X-ray Polarimetry IXPE, made the first detailed measurements of X-ray polarization from a magnetar. The data revealed that the magnetic field structure is even more complex than models predicted, with multiple layers of twisted field lines, creating a magnetic topology that changes over timescales of weeks. Meanwhile, gravitational wave observatories like LIGO are being upgraded to detect the faint signals that might be produced when a magnetar's crust cracks. If successful, this would give us a way to probe the interior structure of these objects directly, testing theories about exotic matter and quantum superfluids under conditions that can't be replicated in any laboratory. What this means for us extends beyond academic curiosity. Understanding magnetars helps us understand the life cycle of massive stars, the physics of matter under extreme conditions, and the chemical enrichment of galaxies. When massive stars die and form neutron stars, including magnetars, they leave behind heavy elements forged in their cores: iron, gold, platinum, uranium. These elements don't just float in space, they become part of new stellar systems, new planets, new worlds. Every atom of iron in your blood was forged in the core of a dying star. Some of those stars became magnetars. You are quite literally made of stardust from stellar cataclysms billions of years ago. The most profound implications emerge when we consider what magnetars tell us about the fundamental nature of matter and energy. Under normal conditions, magnetic fields are generated by moving electric charges, currents flowing through conductors or spinning iron cores in planets. But magnetars challenge this understanding. The magnetic field in a magnetar stores more energy than the star's entire gravitational binding energy. Think about what that means. The magnetic field alone contains enough energy to completely disintegrate the neutron star, overcoming the immense gravitational force holding it together. So why doesn't it? The answer involves a delicate balance we don't fully understand. The magnetic pressure is balanced by the neutron degeneracy pressure, a quantum mechanical effect that prevents neutrons from occupying the same quantum state. But calculations suggest this balance is precarious. If the magnetic field in a magnetar exceeded approximately 10 to the 16 Gauss, just 10 times stronger than observed, the field itself might trigger a phase transition in the neutron matter, potentially converting it into exotic quark matter or other hypothetical states of matter predicted by quantum chromodynamics but never observed. What would happen then? We don't know. The star might collapse into a black hole. It might explode. It might transform into something we don't have a name for yet. Some physicists have proposed even more radical ideas. Dr. Jeremy Hale at the University of British Columbia has suggested that the magnetic fields in magnetars might be strong enough to test predictions of quantum electrodynamics that are otherwise impossible to verify. In particular, the magnetic field might create virtual particle-antiparticle pairs from the quantum vacuum, not as a fleeting quantum fluctuation, but as a sustained phenomenon that could affect the star's observable properties. If true, magnetars would be the only places in the universe where we could directly observe quantum vacuum polarization on macroscopic scales. And then there are the questions we can't yet answer. We've detected approximately 30 magnetars in our galaxy. Statistical models suggest there should be thousands, perhaps tens of thousands, most of them dormant and invisible, their magnetic fields having decayed below detectable levels. Are any of them close to us? Could one wake up? In 2020, SGR 1935 plus 2154 proved that even quiet magnetars can suddenly become active after years of dormancy. What triggers these awakenings? We don't know. Could a magnetar flare affect technological civilization? We don't know. Are there magnetars with even stronger magnetic fields than we've observed, objects at the very edge of physical possibility? We don't know. The most profound implications connect to our place in the cosmos. We live in a universe where the death of stars creates objects so extreme they warp the fabric of space,
break down the quantum vacuum, and release more energy in a fraction of a second than our sun will produce in its entire 10 billion year lifetime. These objects are real. They're out there right now, scattered across the galaxy like cosmic landmines. And every single one was once a star not unlike our sun, just bigger, brighter, and destined for a more violent end. We began this journey with a question. What kind of object could release a burst of energy so powerful it reached across the galaxy and altered Earth's atmosphere in less than a second? Now we know. Magnetars are the universe's most magnetic objects, its most violent eruptions, and perhaps its strangest laboratories for physics at the extremes. They exist at the intersection of quantum mechanics, general relativity, and nuclear physics, a regime where our equations barely work and our intuitions completely fail. What we've learned is humbling. In the few decades since their discovery, magnetars have forced us to revise our understanding of stellar death, magnetic field generation, and the behavior of matter under conditions we cannot replicate or even fully imagine. We've learned that neutron stars can have magnetic fields strong enough to destroy matter at the molecular level from 1,000 kilometers away. We've learned that these fields power eruptions visible across millions of light years. We've learned that starquakes on objects the size of cities can release the energy equivalent to 1 million nuclear weapons. But what remains unknown dwarfs what we've discovered. We don't fully understand how magnetars form. We can't predict when they'll erupt. We don't know if there are objects even more extreme waiting to be discovered. And we're only beginning to understand how they enrich galaxies with heavy elements and influence the evolution of stellar populations. The current scientific consensus is clear. Magnetars represent a brief but crucial phase in the evolution of the most massive stars. They're real, they're dangerous, and they're reshaping our understanding of physics itself. On December 27, 2004, a dead star 50,000 light-years away reminded us that we live in a violent, spectacular universe, a cosmos where the impossible is routine and the extreme is everywhere. Magnetars are proof that nature is far stranger than we ever imagined and far more powerful than we can truly comprehend. The universe is vast, the mysteries are endless, the journey continues.